So obviously the one cell model had some problems. It didn't explain the observations and all of the observations that were coming into the scientific community. So in 1856, this one cell model was revised and a 3-cell model was proposed. It actually took longer than 1856 for the final trappings to be put on the 3-cell model. But the 3-cell model is from another British researcher, Farrell, who took the 3 assumptions and knocked them down to 2. So he again assumed that the Earth was covered with water, wrong. And he again assumed that the Earth was always over the equator, wrong. But he took out the assumption that the Earth does not rotate. Because by this time, Coriolis's effect in his theory was becoming more and more known. Not widely known. In fact, the Germans didn't know about it as of World War I, but it was in some scientific communities. Let's go into the 3-cell model a bit more. The 3-cell model erased the closed loop of the Hadley cell, but did maintain most of the Hadley cell. It actually smushed it down a bit and put 2 cells north of it. In total of these 3 cells per hemisphere, 2 of them are thermally driven and 1 of them is thermally passive or thermally indirect. So let's talk about each of those cells and what this model did for the northern and southern hemispheres. We'll talk about what you already know first. You know about the Hadley cell. You know it was a cell that originated on a thermal drive from the equator. The warm air rose. It went toward the North Pole because the horizontal pressures were lower with the cold air. So it went toward the North Pole. Now, this new model says that it starts to sink down at about 30 degrees north latitude. And the same thing happens in the southern hemisphere. This model starts to sink down at about 30 degrees south latitude. And then this sinking comes around and produces a surface wind that rotates in a circular cell. Okay? So what they are describing here is a warm weather rise and a sinking. So remember we had rising slow, clouds and snow, then surface low. So we can show that here in this revised model. We know that the air will rise. We know that the air will condense, forming clouds, not snow. We're at the equator. But as this moves to the south, it takes air molecules with it, leaving less air pressure over the area where these warm molecules arose from. So that leaves a surface low at the equator called an equatorial low. Remember, rising slow, clouds and snow, then surface low, because everything moves out to the lower pressure area. At the 30s, you notice a sinking sky, warm and dry, surface high. There's a subtropical high at the 30s in this model. And then it comes down in the surface, very much like the trade winds that we noticed from the Hadley cell that were from about 25 degrees to 15 degrees. And they were reflecting the fact that this model doesn't rotate, so you can figure in the Coriolis effect and figure in the deflection to the right for the trade winds. So now these winds become a northeasterly wind moving to the southwest, it describes the trade winds very, very well. This downsized Hadley cell plus Coriolis made sense for that and for many other areas. Let's talk about it. Let me just get my mouse. There it is. One of the other areas where this model made sense was it described the doldrums. Another area that sailors noticed was a dead zone for wind was right around the equator. They stayed away from the equator and they stayed away from 30 degrees, and they tried to run all of their routes with the trade winds between 25 and 15 degrees. And when they wanted to come back east, they used the westerly winds above the 30-degree latitude line. We'll get to that in a second. But they stayed away from the equator. They stayed away from the equatorial low. Because this area here that is rising slow, clouds and snow, surface low, that is a windless area. The reason it's a windless area is because there's no horizontal movement of air in that area. There's no real difference between high and low pressures. You have low pressures from the southern hemisphere of the equator. You have low pressures from the northern hemisphere of the equator. There's really no horizontal differential there that would produce any wind. It's a windless area. It does tend to get showery because you have a lot of clouds rising up in this area with the surface low. So this model explained the doldrums really well. It also explained the rainforests that explorers were seeing when they were colonizing along the equator in the 1800s. So as explorers were working in the Belgian Congo, big rainforest area right along the equator, then when they were colonizing the Pacific Islands, the British were noticing all the rainforests along the equator. The Spanish were going into the Amazon, rainforest there as well. This makes sense because we're talking about an equatorial low that brings in windless, showery weather, perfect for a rainforest. And that explained that phenomena. It also explained the horse latitudes now. So let's move from the equator up to the subtropical high in the 30s. What do we know about a subtropical high? We know that it is sinking sky, warm and dry. Compressional warming dries out the sinking parcel, surface high. In this case, it explains the windless horse latitudes for this reason. Let me show you a sounding from the Jacksonville, Florida area, which is right around the 30th parallel. So it's right in that horizontal line for the 30th parallel. This is a sounding that shows compressional warming. Now you can understand it a little bit better. You see the steep environmental lapse rate here. You see the parcel that is under the environmental lapse rate in a stable, stagnant atmosphere. And you also see an inversion right at 1 kilometer for a stable atmosphere. And the pièce de résistance, you see the dew point drop dramatically in this area. So you know the parcel that has descended here has dried out and left a very low dew point, a dew point with a real difference here. So that is a trade wind inversion, also called a subtropical high. The reason that this inversion is 1 kilometer up is because there is so much convection off of a warm sea. So that convection moves up and the inversion is farther up. We'll go into a little bit more of what this describes. This also describes at 30 degrees latitude the deserts. And the deserts that are there are a dry area as well. And this area is windy. Let's just go over it for a second. This is the Sahara Desert, the Arabian Desert, all along the 30s are Sonoran Desert as well. Sinking sky, warm and dry, surface high. Let's explain why it is windless in those areas. This is from El Paso, Texas, another compressional warming observation here. A very steep environmental lapse rate, a parcel that is sinking, it is stagnant, it is underneath the environmental lapse rate that we see here, so it's cooler, so it's sinking, and a very low inversion here. That very low inversion is also showing you very little wind. Look at, there's no wind basically at the surface. And that makes sense for a very low inversion. Let's explore why it's a very low inversion. This is a 12 o'clock sounding in El Paso, Texas, a noontime sounding, noontime Zulu. That means here it is 6 a.m. In April when this sounding is taken, right after all the radiative emissions overnight, the radiative cooling. This is very, very dry parcel, and you can imagine that in a desert it's going to cool very fast and warm the atmosphere above, leaving the ground very cool. So that inversion is going to be very tight against the ground, and the ground is going to cool very quickly. This wind that you see right above the inversion is for the sand dunes, and actually those sand dunes are blown quite a bit, but while we're at the surface, that windless area helps to support the high sand dunes that are available, that you see in El Paso, Texas. They actually have national parks with their high sand dunes in that area. So the 3-cell model and the revised downsized Hadley cell explained all of these phenomena that people were finding as they traversed into Africa and into South America and into the United States in the 1800s. In addition, and later, the model helped explain the prevailing westerly winds aloft in the upper levels. Because think about it, these air molecules are moving up and rising warm air molecules from the equator, then moving north. And as they're moving north in the upper levels without any friction, the Coriolis effect really takes hold there and it deflects to the right, and this becomes a westerly wind aloft. So it explained the westerlies that we see carrying the clouds, and that's how people knew in the 1800s. They knew there was something about the winds aloft, and now they could explain a little bit more about it when they observed the clouds always moving on a prevailing westerly wind. I think that sums it up. This downsized Hadley cell from the equator to 30 degrees explained the trade winds, the doldrums, the rainforests, the horse latitudes, the deserts, and the westerlies at upper levels. So much more exploration in the 1800s, and this model was serving that from Dr. Farrell. We'll see you on the other side to explain a little bit more.